This video we will study the kinematic curvilinear motion in cylindrical components. In some problems, it is often convenient to express the path of motion in terms of cylindrical coordinates r, theta, c. If the motion is respect to the plane, we can use the polar coordinate r, theta. Okay, as we consider this example. For the case of this problem, the cylindrical coordinate system is normally used in case where the particle move along the t-dimensional curve. That is, we apply theta c coordinate instead of x, y, z, and this is maybe more convenient for this case. So for the case that we consider in plane motion, for the in plane motion, we use the polar coordinate r theta. If we consider this picture, we have the particle at this point as the blue point, and this point can be defined by polar coordinate r and theta, okay, instead of x and y, okay. So actually, if we consider this position, this point, okay, this is maybe point P, okay. If we consider this point, this may be represented by the coordinates, the fixed coordinate system x and y. This if we refer to the red coordinate xy, that is a fixed one. But in some problem, it may be better to define this point by polar coordinate system, that is in the as the blue one, that is r theta instead. Okay, so for this case, r is defined from the reference, is defined as the distance from the reference point O to the particle point P. Okay, so R is always outward from a fixed origin. Okay, the radial direction, R is always outward from the fixed origin. Okay, so it's if we recall for the case of NT, this is the tangent, which is normal for the case of circular path like this. So, but if we compare with the r theta, we found that for the case of r theta, if this is the circular curve, okay, is goes outward from the center of curve, okay, that is opposite to n, okay, and theta is go in the same direction of t, okay, if we compare with the normal and tangential coordinate system that we have learned from previous clip video, okay, and for this case, the radial direction are outward from the fixed origin O, and the transverse coordinate theta is measured counterclockwise as a positive one from the horizontal. Okay, so in case of velocity in polar coordinate, first we consider for the polar first, and then after that we extend to the cylindrical one. That is, we have the c-axis, that is the vertical axis also. So for this case, the instantaneous velocity is defined by v. This is the vector v equal to dr by dt. That is, the vector r represented by ur represent the unit vector in r direction. So then same as the NT coordinate, normal and tangential coordinate. R, theta or polar coordinate is this coordinate is stick on the particle also. It is stick on the particle, so it is not fixed. It is the local coordinate system. So then it is not constant. The UR is depend on the part. It's depend on the part. So then it depend on the time also. So the derivative of UR with respect to time, it is not equal to 0 because it is not constant at any time. Okay, it is not like IJK. So for this case, when we take the first derivative of position vector with respect to time, so we obtain two terms like this. Okay, it is for R and theta, and you will see that for this case, if we compare with NT, tangent is always tangent to the part, and for normal, it's maybe like this. Okay, so for this case, that is not special case as a circular motion. Tangent coordinate and theta is maybe not colline to each other, and R coordinate and normal coordinate is maybe not colline to each other also. So what for this case, we have velocity vector equal to R dot UR plus R DUR by DT. So then we have to determine this term. What is it? Okay. So when we using the chain rule DUR by DT, okay, we obtain DUR by d theta and d theta by dt like this. Okay, and we conclude that DUR by d theta is the direction of DUR by d theta is in direction of u theta by consider this picture. Okay, so the change in UR. So a change in UR with the small angle d theta, we have the directions of delta UR in as the same direction of u theta. And then DUR by d theta become theta dot u theta. Okay, so this means that the velocity vector is composed of two components for r theta coordinate. This is composed of r components and theta component. So then in conclusion, we have V equal to VR UR, okay, plus V theta U theta, okay, Y VR is R dot, okay, and V theta is R theta dot, okay. So for the magnitude of velocity vector become the summation, the vector sum of these two terms of V theta, this is V theta, okay, and this is VR, okay, of these two terms. So if we consider the acceleration in polar coordinates system first, the instantaneous acceleration is defined by dv by dt. We have velocity vector, and the acceleration vector is defined by d by dt of velocity vector that we already derived. Okay, so then we know that dur by dt is not constant, and du theta by dt is not constant also. So then after manipulation, dur by dt and du theta by dt and some manipulation, we can express the acceleration in polar coordinate system is composed of two components, that is the component in r direction and in theta direction like this. So the proof of this equation, you may study from the general engineering mechanics textbook. Okay, that is we is maybe have to divide some term, okay, of dUr by d theta and du theta. Sorry, dUr by dt and du theta by dt. Okay, so in conclude, after we solve that term and with some manipulation, we can find out the acceleration in polar coordinate system composed of two terms, two components, that is the components in r direction and in theta direction. And this term we call the radial acceleration. This is the radial acceleration. And this term we call the transverse acceleration or a theta transverse acceleration. In some case, we may call like the circumferential acceleration. Okay, and the magnitude of the acceleration is the total summation of vector, that is the radial acceleration combined with the transverse acceleration a theta, and we obtain this expression, okay, in terms of the combination, the magnitude of acceleration vector in polar coordinate. In cylindrical coordinate, it is the same as the polar coordinate if we understand the polar coordinate system already. So then for cylindrical coordinate, we define the position vector like this. This is composed of RUR plus CU theta as shown in the picture. Okay, and after that we can derive the velocity vector that is composed of UR components, the velocity in R component, in theta component, and also in C component. And after that, we can determine for the acceleration for R components, theta component, and C component also. That is, we can conclude that the velocity and acceleration for cylindrical components, cylindrical coordinate system is defined by this block. Okay, and next we will study some example for the case of curvilinear motion in terms of cylindrical coordinate.